Well, what you're doing here is that you're doing classic pure functional programming, right? in a very quirky functional language called TypeScript's type system, right? And then and at the end of the day, all you can do is you can make your CPU hot because you have no I/O devices or anything, right? I mean, but this is pure functional programming, absolutely.
I was so lucky to have this opportunity to speak with Anders Hejlsberg, a co-creator of TypeScript in 2012, where he's been the lead architect ever since. He's had quite a career as a language designer even before that, as co-creator of C# in 2000 and creator of Turbo Pascal in 1983. I forgot to mention Turbo Pascal to Anders until after we stopped recording, but there's this fun little lineage of games being implemented in his languages because Turbo Pascal is actually what the very first PC version of Tetris was written in 2 years later in 1985. It's been such a dream to get some time to sit down with Anders and show him this project. We also had some time to talk about other general TypeScript topics, which will air in a separate video in a few days. I've done personal demos of this Doom project to about 50 people at this point, and what I've learned is that it's hard to show it to someone and get a response other than laughter and questions other than what were you thinking. So for this one, I thought it'd be fun to show Anders a bit of the story behind the original ideas and failures I had on how to approach a problem like this. Of course, the long technical deep dive stream is still coming. Wish me luck on getting somebody cool to co-host that. But that video would have skipped over all this history stuff anyway, so I thought this would be a fun chance to touch on it. Anders and I had our other conversation about general TypeScript things first, so this video just sort of jumps right in. Hope you enjoy. So Anders, thank you for joining me. I'm assuming you already saw, I should ask, did you see the video or did you see the announcement?
I saw the video, yes. Very high production value there. That's
Thank you.
Pretty cool, yeah.
You saw my first 3 Blender projects for those animations in my first 3 days using Blender. So if that's not a testament to the power of open source, I don't know what is. So what I thought I would do is walk you through some of my thought process for how I approached this problem.
Mm-hmm.
The most important thing to say about this is that I never believed it would be possible. My wife would sometimes ask me, well, how close are you to finishing this? And I would say, it could be an hour, it could be 10 years. And she'd say,
yeah, and what is this?
How?
Exactly.
Yeah. She'd say, how? And I would say, because all I'm looking for is a reason this can't work. Like, surely this won't be possible. I'm just looking for the specific concrete law of physics that is violated by, by trying to do something like run Doom in a type system. Some people have asked me, how come did you do Pokemon or Tetris or Pong? Did you do some other simpler thing? You went from nothing like this ever before straight to Doom? Why? And that's the reason, is because there were many days on this project where I said, this is it. I finally found it. I finally found the reason this is going to not be possible. And then, some hours would pass and I'd say, well, if I could just do this one other little thing.
Uh-huh.
And I want to show you one of the first major, really big stopping points that I had. So what you have on the screen here is the original plan for how I would approach this. So the thinking was, Doom is kind of deterministic. You can run it in a vacuum. And so that's just like a set of things to compile, like a set of instructions to compute. And what I could do is I could unwind every loop. I could expand every number. I could just unwrap the whole thing. It would be massive, but if I could find a way to chunk things up, it would work. And I did what you basically have on the screen here. Actually, for the longest time, the beginning of this project, I had this kind of syntax where I would just do all of the work for everything in the generics.
Okay.
Because when you start, because TypeScript is, the types is like a functional programming language, there are only expressions. But I really needed a way to make statements. And you can kind of think of like another generic with a default parameter as being like another statement that you can kind of sort of chunk them together. But then you hit the next problem, which is
continuation style. Yeah,
exactly. So then you hit the next problem of like, how do you create a type for this type? It returns something. So then you kind of have this result ending value, and you have this, you type the result, and then that becomes the type of your type, if you so to speak. You're considering these types to be functions.
Yes.
But I hit a really big problem that took me many months to solve. And the problem was control flow.
Yes.
When you have a system like this where you're trying to unwind everything, Well, if you don't know in advance which branch to go down, you end up having to expand every branch. And now we're talking about petabytes is a small number. We're talking about just a preposterous amount of data to be able to do that. And it became clear to me that there would be no chance of actually succeeding if I was going to take that approach. And that's when I had a kind of a breakthrough in a way. This fellow named David Blass, who I think you may have seen on the TypeScript issues. He's the guy that makes Archetype. He suggested to me this kind of basic building block of how to handle the control flow. So I want to show you, I made for you today, I made a kind of the simplest possible example of how this worked. So I want to get your take on this.
Okay.
So here's the smallest way. This is a self-contained file that shows how the whole thing is set up. So I made two instructions. I made an add instruction to add to a string. So the result of this program is a string. It has the program, I'll show you the program state. The program state just has a list of instructions and it has the end result. So we're kind of building up this result. And then, so I have this add instruction and then I have an uppercase instruction. So add has a parameter, you can add some string. So jumping to the bottom to just see how it works, this is kind of the end result, is that I can kind of have a pre-bootstrapped machine that has all the instructions already in there and ready to go. This is not generic at this point. But then I just have a list of all of the things that I want to operate on my result. Then the whole heart, and actually the real, I can show you on the side in a second, but the final kind of state machine thing that pokes the state machine to get it to do another instruction looks almost exactly like this. Where you just pop instructions off, and then you have a kind of switch statement in a sense that looks through those handlers and tries to match it up with a discriminated union. And then you just kind of evaluate, you take the operation on the result, you evaluate each piece.
Each instruction creates a new evolved world. And then at the end you have the final world. Yes.
Exactly. So from there, I realized one of the next big breakthroughs. So I like hurriedly got all the control flow instructions. I went from being totally blocked, just like head in the mud. And then it was like 10 days later, I had every control flow instruction, like select and branching, and just all of it was done. So I was very excited about that. I felt like this really had legs. But then I started running more complicated programs through it, and it started to break because it would just infinite loop. You may have seen in the video, I removed all of the, the limits that are in there, the recursion limit and all of those things. And so the next innovation that I'm very proud of, and I kind of made it simpler here. There's, as you know, people who do crazy things with TypeScript are very bitter that there's no way to do addition in the type layer, which, by the way, I am not bitter about. I don't think we need that. I don't think it's that useful. And you could put me on record as saying those people should be satisfied with what they have. But one of the ways people do that is to just make an array of ones. And that's, you can take the static length on that array and get a counter. So what I did here in this version, it's the same file we saw before, but I modified it a little bit to stop at a particular point. So I can pass optionally, I set it to 1,000 to have a big number. So now we have our program. This is exactly the same program before, and we can run it without giving it a place to stop. But now what we can do is we can stop it. I can pass this other parameter here, and we can say, do the first instruction and then stop. Do the 10th instruction and then stop. Does that make sense? Are you following this part?
You mean you can run 100 instructions or whatever, stop, and then boot yourself into a next type that runs the next 100. Is that what you're saying? And then avoid the limiters. Yeah.
And so when I say, people ask like, okay, how could this possibly work with vanilla TypeScript? It's because what I basically did is I created a machine that can pause itself and spit out its guts. And it's just a TypeScript type. So, the whole machine itself, in this case, it has count, instructions, and result. But I want to show you now, this is a good segue to show you the end, the kind of like, so this is the real deal, full execute instruction thing. The only thing that I added here was a debug mode so that I can, because we have this concept of the result or like the object that contains all the guts. So I can kind of tell it that I want you to calculate the result, or I want you to give me the guts in full. And then I implemented a halt instruction so that I can go anywhere in any program and add, and the halt instruction just says halt. There's nothing fancy in there. And then the machine knows that, oh, if I hit a halt instruction, I'm supposed to stop.
Yeah, yeah.
And that is the way. So if I go to types here, I'm going to show you the full program. This is the full state. So the one we looked at before had count and instructions and result. And this has those three things, but it has a lot more things for all of the other stuff that I need. So just pausing there, like, if you were to do something like this, what are your thoughts about this approach? I'd love to hear your reaction to this.
Well, what you're doing here is that you're doing classic pure functional programming, right? in a very quirky functional language called TypeScript's type system, right? And then and at the end of the day, all you can do is you can make your CPU hot because you have no I/O devices or anything, right? I mean, but this is pure functional programming, absolutely. And we certainly know that TypeScript's type system, in its Turing completeness, is a pure functional programming language. And you can sort of see, you can even start to analyze the things that were qualitatively missing as a functional programming language. Like when you think of it as a functional programming language, the values in that program are types. And the functions in that program are generic types that take type arguments, which are your parameters, right? That can be evaluated. The statements are your conditional your conditional types and your index access types and whatever, and so.
Right.
But qualitatively, you can also see what we're missing. Like we're missing higher kind of types, for example, which is the ability to pass functions to functions, right? That is something that functional programming languages generally have as a first-class concept, but we don't. And so,
are you aware that people have found a trick to be able to do?
Oh, sure, yeah, the HKT, yep.
So I actually, in the beginning, I thought that I would use higher kind of types, but I think it had more to do with how WebAssembly works than anything else. That I didn't end up needing to go that. I mean, I'm very passionate about HKTs and I love that stuff, but there was no opportunity in this project to do something just for the fun of it. It was very much like, the performance of all of these things was a big consideration. I pulled up on the screen here one of the control flow instructions. I think this is one of the simpler control flow instructions. And, they are exactly like you said. They're just, at the end of the day, you get to this point where you feel like you're creating functions. And I would get into a state of mind where it's like, I'm just writing someone joked to me that calling this TypeScript is kind of a stretch. And I think,
yes,
I think we have to agree,
But I will say this certainly qualifies as a highly conclusive proof that we're Turing complete, right? I mean, not that we didn't know that already, but yeah.
I think it's funny because I have to admit that that's true, but in my heart, people would say to me, I think one of the things that kind of egged me on to do this project is people would say like, well, but of course it can run Doom, it's Turing complete. And I would think that's baloney. Just because it's Turing complete doesn't mean it will finish in in a human lifespan.
Right. No.
I think like what I say to people is, if this project, if this video and everything were announcing it were the same, but the result was it could run, but it will take 1,000 years, would it be as cool? And I think the answer has to be no, right?
Well, I mean, but how long did it take? I mean, it took a while.
It took 12 days.
Yeah.
I can tell you that like about 60% of the time was simply turning this type into a string in order to dump it to a file, or because it was done in a virtual file. It was type checked in a virtual file system where we kind of pause and then dump the TypeScript file and then evaluate it again with the type checker. So I hear that part got a lot faster. So I'm expecting that. But the other part where it got, it was very where the performance really ended up mattering was in the memory. So this is why I created the L1 cache situation, is because the more I added to memory, the longer it took. And it got to a point where it was like asymptotic. I don't know. exponential is the word I'm thinking
Yes,
of, where
yes.
it would just go off, and at a certain point, my instruction rate went from 500 instructions per second down to 1 instruction per second. And
Right.
at that rate, we're never going to get to millions.
No.
And so there were a few things I did, like I did a memory compression situation where, if you notice here, there are no 0 bytes. So anytime that I encountered a 0, I would just disregard it. And anytime I read from memory, if it's not there, I just assume that it was written in the past and it's a 0. And that ends up working out because the way WebAssembly works is it initializes all of the memory to 0 at the beginning of the program. So hey, there you go. And then I created that L1 cache where, let's see, L1 CAC, yeah. Where the L1 cache is basically the same working pieces as the regular memory, but there's a garbage collector that will come through every few. So you see the L1 cache does have some zeros in it. Mm-hmm. So it's uncompacted. And so the garbage collector can come through every once in a while and kind of rectify the states, but I can configure it to only do that every 1,000 instructions or whatever, all at the type level. So, yeah, I mean, I think I'm very flattered that people responded positively to it. I think there's some exciting things that I would like to see. Like, one of them is having these type level errors. Like, I think if we squint, there might be a way to create something at the type level in userland that kind of vibes, can kind of build off of this situation where this evaluation of a complex type will do it in pieces and then it will stop itself. So if the program hits an error, so like we have branch table, well, one of the things about branch tables, there should be something on the stack. And if we hit a situation where there isn't something on the stack, it will halt. And this state.error instruction is just a pass through for halt that adds some information to it.
Yeah.
So, yeah. But in the end, I created a dashboard, and I think this is something that I think is really a cool thing about this. So I have this return mid loop. It's just a mid loop. It's just I wrote this WASM. I hand wrote this WASM program that does some funny looping stuff, and it returns in the middle of a loop to check some control throw stuff. Well, what I can do here then is I have it stopping at the 11th instruction. I can just put 12 in here, and you'll see that at the bottom, we're going to see all of the instructions update for what the next instruction is. So I'm kind of dumping out. You see I have true as to say debug mode, and then 12 is the next instruction. So I can say 14 or whatever, and it's gonna push in the next value. I just restarted it. So here, we'll see if it will play ball for a second. And this was the way that I debugged a lot of things that I built piece by piece.
Yeah.
The final thing I want to show you that I just think is a testament to how to build something like this is a lot of people ask me, like, how did you make sure that it didn't break anything? And the way was that I tested everything 6 times with the same inputs and outputs. So we see here, I'm going to go to this, we can go to a comparison instruction. So this is I32 equals. What I did was I made this comparison test case file that has all these different test cases so there's an A and a B, and then I have all the different results for signed, greater than, unsigned, greater than, whatever. And then I do the same thing again, this time all in binary, right? And this one's easy because binary true, you can kind of binary true and binary false. Yeah. So what I did was I ran it through 6 times. I'm going to skip showing you the 6, but I'll show you the last 2 here. The first 4 are just plain JavaScript binary, plain JavaScript decimal, plain TypeScript binary, plain TypeScript decimal. But then I also created WebAssembly programs that run through that the smallest possible program that really does that instruction, so that I could exercise the TypeScript WebAssembly or the JavaScript. I'm sorry, we're going to the wrong file. That will exercise the JavaScript WebAssembly runtime. So I take those same exact inputs and outputs and I run them through that. Mm-hmm. And doing this, I found all kinds of errors, things that I would never have expected, or I didn't know anything about two's complement and VMs, and I'd never touched WebAssembly before this. But anyway.
Well, I'm sure you know a lot about WebAssembly now.
I sure do. Yeah, I mean, it's been a journey, and I'm very excited to share this story with people. And it's fun to be able to just show you something like this. I mean, did you ever think, I mean, I guess the answer has to be no, but it was no for me anyway. I never thought this would be possible, but when you started on this journte, did you ever think something like this would be possible?
No. And nor did I necessarily intend for it to be possible, but I am proud that it's possible. I mean, that does sort of demonstrate that there's some level of stability in our in our implementation, that this can be done. But I think also I'm happy for you, because this is basically a journey of you're not an electrical engineer, right? But this is a journey from literally the very bottom all the way to, you certainly know how the whole stack hangs together now, right?
I had never written C before, and in this project is my first C program. I did I did Conway's Game of Life in C, and it was very intimidating. But there were so many things. I'd never worked with Clang, and I didn't really know what LLVM was, and I had no concept of what a fun thing. I'll show you one little last thing that I think is really cute. Is you have a 50-50 shot of making it little endian or big endian. And I actually didn't really know what Endian, I'd heard the words Endianness, but I didn't intuitively understand what it was. And I lost the coin flip, and I implemented the whole thing big endian on accident.
Oh, really? Yeah.
And WebAssembly requires little endian. It's kind of built into the way that
okay. I didn't even know that, but yeah.
So it doesn't end up mattering. And actually, I got very far along before this came up. And it wasn't until I was doing memory instructions that handle pieces of memory. So you have this memory instruction here, I32 load 16U is saying take half of take 2 bytes of the 4 and make it a number. Well, then suddenly I was getting really wonky results and I couldn't figure out why.
Yes. Yeah.
And the answer was that I implemented it big endian. And it was only after I fixed the bug and I realized wait a second, is this what Endianness is? And I Googled it and I was like, oh man, that's what it is. Okay, that's the order the bytes are stuffed in. But because I stored them in reverse and read them back in reverse, and I was only dealing with 4 bytes at chunks at a time.
Yep.
It always worked out. Thankfully, this is, I think, really funny. The only thing I had to do to switch the whole system from big endian to little endian was change the order of these 2 lines here. This is the general purpose place where I push memory in and read memory out. So I just read it in a different, in the opposite order from beginning to end or end to beginning. And there it is.
That is funny.
There's lots of stuff like this it's just like you said, I really did come from the ground up. And frankly, I'm not going to test it because I promised myself that I wouldn't keep going on this project. But I think that this would have been possible back in TypeScript 4.1. I didn't really use many super advanced features of TypeScript types. I used string literals is really the main.
But you use recursive conditional types, right? Or so.
Yes, I did. Was that okay? So
yeah,
does that push us a little later?
There were tricks you could do with index access types, and that was actually where that was the first place where Turing completeness got introduced, and that was even before we allowed self-referential conditional types.
Gotcha.
But I think they came later. Well, maybe they were. I can't remember. It's been so many.
But it's been a while that this has actually been possible, because there's really.
Oh yeah.
It's all based upon string literals and being able to add and remove to them and iterate them. So, and that was another funny thing, that you had to. Some people ask me why did you have to implement all the algorithms in reverse? And it's just TypeScript designers had a choice to make. If you iterate it, if you parse through a string, should you go start from the left or start from the right? And they chose to start from the left as a reasonable choice. And so I tried really hard, actually. I left it in the code. I didn't even realize I left it in the code base, but I tried very hard to figure out a way to do the binary operations from the other direction. But you end up needing a window that you could possibly expand all the way to the length if you have a carry from the very beginning of the number. At that point, it's well, I guess we might as well just do it in reverse anyway.
Yeah.
But anyway, so much more I could show you, but I just want to say, from the bottom of my heart, thank you so much for you and the team. I think what's cool to me about TypeScript is actually not just the language. I think what's cool is how functional and how dedicated the team is. I know people leave their jobs for lots of reasons, but the sheer dedication that, there's so many people on the team that are, that have been on the team for many, many years, and yourself included, of course. I think it's a testament to the energy and the commitment and I can't put words to it. I'm just so in love with this language, and I'm so thankful that you all take the time to make it as excellent as you have. And
I appreciate that.
Yeah. Thank you.
And I will say it's an excellent team, and a lot of the credit for all of what we've talked about today goes to our team. Obviously, I mean,
Absolutely.
if it wasn't for the team, and yeah, I enjoy working with these people every day. It's such a privilege. Yeah.
I'll close with saying, if anybody asks for an issue, if there's a bug report in the future or an issue where a feature request where anybody's asking for something and using Doom as a justification, please tell them I said TypeScript is good enough. Let's just do better errors and performance for the rest of time, and I'll be happy. We can never get to the finish line on those, but I think this is such a wonderful type system, and I'm very satisfied with what it has. So thank you so much.
Thank you.